So it's my pleasure to introduce Andrew Stocker from University of Colorado Boulder, who will talk about synchronizing dynamical systems, which I understand is part of his PhD work, which he should defend in a week or two.
Yeah, about 2 weeks.
Excellent. Well, we're looking forward to your talk, so take it away.
Thank you. Yeah, thanks for inviting me to the seminar. Happy to be here. So yeah, I'll be talking about synchronizing dynamical systems. Feel free to ask me questions. I should see chat messages, but if I don't, just feel free to interrupt as well. So yeah, rough outline of the talk: introduce dynamical systems, briefly talk about how we build Cstar algebras from, in particular, expansive dynamical systems. Then I'll talk about this particular type of expansive dynamical system called the synchronizing system, which has been the focus of my thesis research. And then we'll build up this example of a dynamical system called a shift space, and then we will actually construct the Cstar algebra of the shift space dynamical system, and we'll use a Bradley diagram to do that and produce an AF algebra. And then I'll also talk about just some of the other results that we've obtained for expansive dynamical systems. Okay, so the motivation is that so Smail Spaces are this class of expansive dynamical systems that are very well understood. So a lot of work has been done by Ian Putnam and Jack Spielberg, David Ruel, many others on Smail Spaces, and also the Cstar algebras that can be constructed from them. Subsequently, Klaus Thompson constructed Cstar algebras for the general class of expansive dynamical systems, which generalize Putnam's constructions. But so a Smail space is a specific type of expansive system, but in the general expansive system case, these Cstar algebras are not so well understood. So the goal of my research has been, how can we extend these Smail space techniques to the more general study of expansive dynamical systems? Okay, so just some definitions. For us, a dynamical system will mean a compact metric space and a self-homeomorphism of that compact metric space. So we'll usually call these X and phi. And then, so what does it mean for a dynamical system to be expansive? Well, this is the definition right here. It just means that there exists this constant, which we call the expansiveness constant, such that two distinct points in the dynamical system can't remain within epsilon x of each other for their entire orbits. So this is written here in the contrapositive. So it's saying that if the distance between all the iterates of x and y's are within this expansiveness constant, then this implies that the 2 points are the same. So if you want to think about this in a different way, it's really a topological version of the concept of sensitivity to initial conditions in the field of PDEs. So expansiveness is telling us that our orbits of distinct points cannot remain close for all time. So that's what an expansive dynamical system is. And then we have two other definitions which will come up. So defining them here. So a dynamical system is called irreducible. If for every pair of non-empty open sets U and V, you can iterate the dynamical map enough on U such that you have a non-trivial intersection with V. And then we also have this equivalence relation called either stable or unstable equivalence, depending on which one you choose. And so stable equivalence of 2 points means that their forward orbits eventually converge to each other. So this is written here. So as all the iterates of x and y go towards the limit as n approaches infinity, they get asymptotically close to each other. And then likewise for the backwards orbits. Just take a sip of water. Okay, so a Smail space, I'm not giving the full definition here because it's quite long, but heuristically, a Smail space is a dynamical system which is locally hyperbolic, in the sense that every point in a Smail space has a neighborhood which is homeomorphic to a stable and unstable direction. So by that, I mean that, so here we have this point x and some neighborhood, which is drawn as a square. And we have a bunch of points here that form an axis. And on this axis, all those points approach x asymptotically as we iterate phi. And then on this perpendicular axis, we have a bunch of points that asymptotically move away from x as we iterate phi. And what we're saying for a Smail space is that every point has a neighborhood which is homeomorphic to the Cartesian product of these two axes. So here it's drawn as if these have the topology of a line segment, but really the topology on these local stable set and unstable set can be anything, but in a Smail space, every point has a neighborhood that is a Cartesian product of these two directions. And so we'll see more later on about why this makes sense, but this is the idea of a Smail space. So this is what we mean by locally hyperbolic, because it has this contracting and expanding direction. So an easy example of a Smail space are given by these so-called hyperbolic toral automorphisms. So to construct one of these, you start with a matrix. So we'll just do one example, this matrix 2, 1, 1, 1, which is like the Arnold cat map, if you've seen that before. So this is a matrix acting on R2, but because it's determinant 1, it's invertible over the integers, so it actually induces a homeomorphism of the torus once we quotient by by z squared. So I apologize, I'm kind of sick today, so if my voice goes out, such is life. So the interesting thing about this homeomorphism is that because the matrix A has these two eigenvalues, one that's between 0 and 1 and one that's greater than 1, this gives the homeomorphism an expanding direction corresponding to the eigenvector corresponding to the unstable eigenvalue, lambda sub u. And it also has a stable direction or contracting direction from the eigenvector corresponding to the stable eigenvalue, lambda sub s. And so in this case, on the torus, we actually do get expanding and contracting directions where every neighborhood is homeomorphic to a Cartesian product of these two directions. Okay. So in more generality, the way that we construct Cstar algebras from expansive dynamical systems, I mean, the recipe is probably familiar to a lot of people, but the idea is that we define this equivalence relation on the space. We will topologize this equivalence relation in a way that gives us actually an étale groupoid, and then we form the groupoid Cstar algebra from that. So in particular, the equivalence relation that we're going to be dealing with is called local conjugacy. And local conjugacy is going to be a form of asymptotic equivalence, but that preserves the local topological structure of the space. So the way we encode this is we say that 2 points are locally conjugate if there's a neighborhood of X and a neighborhood of Y and a homeomorphism called gamma from U to V from between these two neighborhoods that fixes X, or rather it sends X to Y. And then what we want is that we want these 2 points X and Y to be asymptotically equivalent, but uniformly on their neighborhoods. So we write this as this limit of the soup. So this is saying that the limit in the forward direction, so as n approaches positive infinity, is uniformly, these two neighborhoods get close together. And then this is also true in the negative direction. So remember this stable and unstable equivalence that I talked about before. This is like a combination of those two, but we also have this compatibility of the two neighborhoods of X and Y. So this equivalence relation, we can denote the set of equivalent pairs as GLC. So for LC for local conjugacy of the dynamical system X phi. However, we don't want to use the subspace topology to topologize this set. We actually want to define a subbase, which is given by the pairs Z, gamma Z. So U, V, and gamma are coming from this local conjugacy that we've defined. So if you consider all local conjugacies on the expansive dynamical system, and then define neighborhoods of X and Y to look like this, then this actually determines a subspace, or sorry, subbase for the topology on GLC, which actually makes it an étale groupwood. So we define the homoclinic algebra of X phi, this expansive dynamical system, to be this reduced groupoid C-star algebra. So we denote this by A. So this is the main C-star algebraic construction that we work with. Thompson also defines these heteroclinic algebras, S and U. S and U are for stable and unstable. And these are essentially a similar equivalence relation, but only for positive or negative iterates of phi. So if you notice on the previous page, this limit is to positive or negative infinity, and the stable and unstable algebras are either for positive infinity, negative infinity, but it turns out that there's actually a lot of subtleties that come up if you only want to consider asymptotic equivalence in one of the two directions. So the construction of these two heteroclinic algebras is a little bit more involved. But I will note that so Ian Putnam originally constructed stable and unstable algebras for Smail spaces, and these also generalize those two algebras. And yeah, and then the construction of these requires a dense set of periodic points. So it's not true in general that an expansive system has a dense set of periodic points, but we'll see that these synchronizing systems that I will define do in fact have a dense set of periodic points. Okay.
If you assume something like irreducible or non-wandering, do they then maybe have dense periodic points? Even then, is that not possible?
Yeah, I mean there are minimal expansive dynamical systems. So yeah, I think
that answers the question then, I guess.
Yeah. So yeah, there are some weird cases, but for the synchronizing systems, it's enough to assume irreducibility, and then that gets you a dense set of. Actually, it's actually just enough to assume non-wandering. Yeah. So all right. So just some background on Smail spaces. So we'll have a slide later on some of the parallel results for synchronizing systems, but Ian Putnam showed that actually, so you need to assume that the Smail space is mixing, but so the tensor product of these heteroclinic algebras, the stable and unstable one, are actually Morita equivalent to the homoclinic algebra. Additionally, he showed that the homoclinic algebra is what's called asymptotically abelian. So I have a definition of it at the bottom here, but it means there's a natural sort of induced star automorphism by the dynamical map. And the Cstar algebra with this star automorphism alpha is asymptotically abelian if this limit is 0. So this is a useful property. And then just in general, these three Cstar algebras, the homoclinic and heteroclinic ones for a Smail space, are just very nice Cstar algebras. So they're simple, separable, nuclear. They have a unique trace. They have a lot of just very nice properties. So our goal for the synchronizing system has been to at least, get some of this list, but we'll see that there's complications. Okay, so let's define synchronizing systems. The idea is that, so Smail space, every point in it has this local product structure. For a synchronizing system, we want like enough points that have local product structure, and maybe we allow for some points that are singular and don't have product structure, but we want at least enough. We'll see that synchronizing systems have a dense open set of these like nice points that behave like they're in a Smail space. So the idea is that we have these local stable and unstable sets. We can define them rigorously as follows. So we can just look at all points that y such that the forward iterate of y stays close to the forward iterates of x. Likewise, we can look at points y whose backwards iterates stay close to backwards iterates of x. And the crucial point is that if our dynamical system is expansive, then if for epsilon small enough, this intersection can only consist of one point at most if it is non-empty. So you can see that because if you have 2 points in here, all their forward iterates will be within epsilon sub x, this expansiveness constant, and so will the backwards iterates. So by this expansiveness condition, they have to actually be the same point. And so basically, we want to define this set D sub epsilon, which consists of all the pairs of points in the space such that this intersection is non-empty. And by expansiveness, it's just consists of exactly one point. So we can define a function from D sub epsilon to x that sends a pair xy to this point in the intersection. So if you'll allow me, I'm just going to kind of go back a couple slides to this diagram. So in this diagram, this axis right here is xu, x epsilon. And this axis right here is x s, x epsilon. And this bracket map, what it's really encoding is if we have some y here and some z on this axis, the bracket map will sit at the point that is encoded by these two coordinates, so to speak. So if we have a point that has this local product structure, this bracket map actually gives us this homeomorphism that we're seeking. The homeomorphism of the neighborhood to the Cartesian product of the stable and unstable directions. So, and then this D sub epsilon set, it's closed. It contains the diagonal. The bracket map is continuous. So the technical definition of a synchronizing point is essentially a point where the bracket actually gives this homeomorphism onto a neighborhood of X. So this homeomorphism is from the Cartesian product of the unstable and stable direction to a neighborhood, which we usually call a rectangular neighborhood or a product neighborhood, something along those lines. But yeah, the gist of it is that these synchronizing points behave like they're in a Smail space because they have this product neighborhood. So the synchronizing system is an expansive dynamical system which has at least one synchronizing point and is irreducible. So by irreducibility, we actually get that from this one synchronizing point with a rectangular neighborhood, there exists a dense open set of points that are also synchronizing. So Smail spaces are synchronizing systems where every point is synchronizing, which makes sense from our heuristic definition. My answer to Karen's question, there are expansive dynamical systems that are not synchronizing. Yeah, we know that synchronizing systems have this dense set of periodic points. So hence, like a minimal expansive system, unless it's just a trivial one, cannot be synchronizing. A lot of the motivation for these synchronizing systems have come from the study of symbolic dynamics. There are these things called synchronizing shifts, which I will talk more about. That's been, synchronizing systems are sort of a merge of Smail spaces and symbolic dynamics. Okay, and so this is some results that we've gotten so far to parallel Ian Putnam's results from previous slides. So the interesting thing is that so Robin Dealey is my advisor. We've been working on this together. The synchronizing points determine an ideal in the homoclinic Cstar algebra. So it turns out that the property of being synchronizing is invariant under this local conjugacy relation. So we get this ideal in the Cstar algebra. We've also shown that the homoclinic algebra is also asymptotically abelian. And then, this Morita equivalence, so one might expect that since the synchronizing points behave like they're in a Smail space, this ideal would be Morita equivalent to some analog of the stable and unstable algebras. It turns out this is only true in a slightly restricted case called a finitely presented system, which I haven't talked about and I won't talk about too much, but finitely presented systems are synchronizing systems that can be covered by a finite number of these product neighborhoods. So these square neighborhoods that I've been writing that are homeomorphic to this, the two unstable and stable directions are called product neighborhoods. And if you can cover your space by a finite number of these, then your system is called finitely presented. In particular, all Smail spaces are finitely presented. But so if we have, actually we need to assume mixing here. So if you have a mixing finitely presented system, and then we have this caveat that we need to also assume that the groupoid is amenable, although we're fairly certain that this is true in general, then we get this analog of the Morita equivalence. And we also get that this ideal determined by the synchronizing points and the stable and unstable algebras are simple. So these are analogs of the result from first Smail spaces. So in this sense is what we're saying, that these synchronizing points behave like they are a Smail space. Okay, so sorry, I should ask any questions so far before we kind of pivot. Okay. So I have not given an example of a synchronizing system yet, but the the main example that we'll be talking about is what's called a shift space. So before we talk about that example, I need to build up some concepts of shift spaces so that we can talk about it. So what is a shift space? So first, we consider a finite set A, and this is usually called an alphabet for the shift space. And then we can form the set of all bi-infinite sequences where every entry of the sequence is in this alphabet A. And we give this the product topology. So it's a compact metric space that's totally disconnected, like a Cantor set. And then we have a homeomorphism of this space to itself called the shift map, which takes a sequence and just shifts it to the left. I don't know if it's flipping my camera, but so it's shifting this sequence to the left. So a shift space is it's a dynamical system, and it actually turns out to be expansive, but it's a closed subspace of A to the Z, which is invariant under this shift map. So shift spaces are a very rich class of examples, and they're very interesting in their own right. The whole field is called symbolic dynamics, but in particular, we use them a lot in expansive dynamical systems. It actually turns out that every expansive dynamical system is, in some sense, like a quotient of a shift space, which is interesting. Yeah, and then the second part of the definition, a lot of times we'll talk about the language of a shift space, which is just the set of finite words that can appear in any element of X. So we think of, yeah, this shift space X coupled with the shift map as a dynamical system. So, I mean, we've already talked about a couple examples of expansive dynamical systems. So if every shift space is expansive, then what are the shift spaces that are Smail spaces? What are the shift spaces that are synchronizing? So it turns out that the shift spaces that are also Smail spaces are these shifts of finite type. And these are constructed by looking at all sequences in A to the Z that don't contain some words, and you specify a finite set of these words that are forbidden. And these shifts of finite type also correspond to actually edge shifts on finite directed graphs, which is interesting. So just a couple easy examples. So the full two shift, we just take every sequence in the binary alphabet. So the full two shift is just the entire subset of the alphabet 0, 1 to the Z. So the set of forbidden words is empty in this particular case. A non-trivial example of a shift of finite type is this golden mean shift. And this is the set of all binary sequences which contain no consecutive ones. So the forbidden word, in this case, there's just one, is just two consecutive ones, because that's all that you need to forbid in order to get all these sequences that don't contain consecutive ones. So those are two examples of shifts of finite type. Shift spaces that are synchronizing are called synchronizing shifts, naturally. An example of one of these that we're going to work with is called the even shift. And the even shift is the set of all sequences in the binary alphabet which have an even number of consecutive zeros between any two ones. So the even shift is not a shift of finite type, because you have this condition that we have to forbid all words that are a 1 and then an odd number of zeros and then another 1. Okay, so we'll talk more about the even shift. So if you're not too familiar with the topology on spaces like this, so two elements of a shift space. So if you have two of these bi-infinite sequences, we consider them close if they agree on a large window around the 0th index. So we write this window as like X subset this interval from -n to n, and really it just means the finite word in the infinite sequence given from the -nth index to the nth index. And we say that X and Y are close if these two windows agree. And of course, if they agree for all n, then they're actually the same sequence. So X and Y are getting closer if this window is if these windows are equal for larger and larger n. And so we've talked about stable equivalence and unstable equivalence. So because of the way that the shift map is defined and the way that the topology is defined, 2 points are stably equivalent in a shift space if simply the sequence agrees at some point in the future. So if there exists a big N such that all the entries are the same for n larger than big N, then these 2 points are stably equivalent. Sorry. And likewise, we have a similar definition for unstable. And so the the local stable and unstable sets are defined similarly. So this is basically the set of all points that are unstably equivalent to X for a certain n that depends on epsilon, and likewise for the unstable set. Okay, so now really what we want to talk about with shift spaces is this local product structure that we've been talking about for expansive dynamical systems. So what does product structure look like for a shift space? Okay, so this is what the bracket map does for a shift space. So if we have 2 points, Y and Z, where Y is unstably equivalent to X for some delta, and Z is stably equivalent to X for some delta, then what the bracket map does is it takes these two sequences, Y and Z. So Y is unstably equivalent to X. So we know that for all entries less than n, Y and X have to agree. So I've written that in the sequence here. And Z is stably equivalent to X. So likewise, Z has all its positive entries or greater than -n entries equal to X. And what the bracket map does is it takes this right tail of Y and the left tail of Z and glues them together to this window here. So if a point X is synchronizing, so it has this local product neighborhood, then for some n large enough, what this is essentially saying is that anything that can happen before this window here and anything that can happen after can be glued onto X minus n to n. So this is sort of another perspective on what the bracket map is doing, is it's saying that there's this word here such that anything happening before it doesn't depend at all on what happens after it, because no matter what this is and what this is, there always exists an element of the shift space where we can sort of glue these two things together. And this is the original definition of a synchronizing word in symbolic dynamics, is that a word W is synchronizing if you can add U on the left and V on the right, then UWV is also a valid word in the shift space. So this bracket map sort of gives a generalization of that. Okay. And then lastly, we'll talk about this local conjugacy relation. So the local conjugacy, we'll see that it sort of preserves the product structure in the sense that X and Y are locally conjugate if for some n large enough, we can look at the neighborhood of X, which consists of all points that look like this right here. And we have a bijection from points like this to points like this in the neighborhood of Y. So essentially it's taking any tail in the unstable direction that's sending it to a point that also has the same tail in the unstable direction, and likewise for the stable direction. So the whole idea is that we want to construct this homoclinic algebra for a shift space. And because of the topology on the shift space, we can do this with a Bratley diagram, and we get an AF algebra. So I will construct this in the example of the even shift. Okay, so I've just said a lot, so let's consider a example. So the even shift I've already mentioned. It's this shift space where between any two ones, there can only be a even number of consecutive zeros. In other words, we have to forbid all the words of one with an odd number of zeros and then another one. So this is a shift space because this condition on the sequences is a shift invariant condition. So the even shift is what's called a Sophic shift. So just a particular class of shift space that also happen to be synchronizing. Okay, so the even shift is not a Smail space. So every point, we can't have that every point has product structure. But the even shift's a nice example because it turns out that almost every point has product structure except for one point. And this is this point here with all zeros in it. So let's see why this point is not synchronizing. So it turns out what you can always do is you can always take some X that's unstable, locally unstably equivalent to the point of all zeros, and some Y that's stably equivalent. So I've taken, for example, this point here and this point here. And what turns out to happen is that the bracket of these 2 points cannot exist, because if you try to form the bracket, what you end up with is this point, which is not a valid point in the even shift. And you can see that we can always do this for a larger and larger window of zeros. We can always sort of insert a 1 on the left-hand side and a 1 on the right-hand side, and kind of screw up the local product structure of this point of all zeros. So this point of all zeros cannot have a product neighborhood, and it turns out to be the only point that's not synchronizing in the even shift. So so I mentioned that we can use a Bratley diagram to create the homoclinic algebra for the even shift. So this is the Bratley diagram right here. So if you haven't seen a Bratley diagram before, what it consists of is like an indexed collection of vertices and also an indexed collection of edges. And we draw it usually as levels, and then the edges always go from one level to the next level. So here, each level consists of words of length 2n plus 1, and then the edges from one level to the next are given by appending two symbols on the left and right. So for example, here we add a 0 on the left and a 0 on the right. Here we're adding a 1 on the left and a 1 on the right. Let's draw one more. So from this edge here to this one, we are adding, say, a 0 on the left, 1 on the right. So why does this reflect the local conjugacy relation on a shift space? Well, each vertex here is given by words that are equivalent up to whatever you can add on the left and the right. So because in the even shift, after we have an even number of zeros, we can do whatever we want after that because we have no conditions on the right. These three words of length 3 are equivalent. This word is not in the same equivalence class because there's this odd number of zeros on the right-hand side. So these four equivalence classes depend on the parity of the number of zeros on the right and left-hand side, because that determines what words you can add on the left or the right. And then the word of all zeros sits in an equivalence class lonely by itself. This gives us in the sort of like an inductive way to create all these local conjugacy classes, because what this gives us is if we have two elements x and y in the even shift and say that the window from -2 to 2 around x looks like all ones, and maybe the window from -2 to 2 around y looks like 0, 0, 1, 0, 0, then there's actually a local conjugacy between those 2 points, because there's a bijection between the words that you can add on the left and right of all ones and the words that you can add on the left and right with this particular word right here. And so this Bradley diagram gives us an AF algebra, which in this particular case is the homoclinic algebra of the even shift. And so it's interesting on this diagram, you can see this ideal of synchronizing points, because all the paths that eventually go through one of these 4 vertices on each row, these all have to be synchronizing points. And then we've shown that the only non-synchronizing point is coming from the sequence of all zeros, which is just this single point on the right-hand side here. And so it's yeah, you can see the synchronizing ideal straight from the Bradley diagram. So yeah, so in particular, we can compute the K theory, or in particular the K0 group of this homoclinic algebra of the even shift straight from the Bradley diagram. So the way this goes is you compute this direct limit of abelian groups. In this case, we have 5 vertices at every stage, and then the edges between consecutive stages, it stabilizes after this row here to be the same as the edges from this second row to the third row. And so this edge relation is encoded by this matrix here, this 5 by 5 matrix with integer entries. And the K theory of the homoclinic algebra is this direct limit of just applying this matrix P over and over again to the free abelian group Z to the 5th. Okay, so the even shift is a nice example of a synchronizing system. because it only has this one non-synchronizing point, and every other point is synchronizing, and hence it has this product structure. Any questions so far?
Maybe you already said this, but is it that all shift spaces are synchronizing or no?
No. So actually, the example that I know of a minimal expansive system is a shift space called a Topology flow. Yeah, shift spaces sort of like in every sort of subclass of expansive system, there is a shift space representing that subclass. Not in like a rigorous way, but shift spaces can kind of be as complicated as any expansive system. Yeah. Yeah, and I unfortunately don't have time to talk about Topology flows. They're interesting, but the methods that we're talking about here, unfortunately, like don't apply to them because they're not synchronizing. So, but yeah. But you can compute a Bradley diagram similar to this for any expansive system, though. It just turns out that in a lot of examples, the local conjugacy relation sort of fails to give you useful information. Like for the even shift, the Bradley diagram is very nice because it sort of stabilizes in this way. But there's examples where the Bradley diagram just gives you continuous functions on the shift space, so it's just the trivial relation. Yeah. Okay, so here's another example, which we won't talk about for as long, but is also interesting. So this shift space is formed from this countable graph here, and because this is a countable graph, we actually have to take a closure of the set of all bi-infinite walks on this graph in order for it to be a shift space, because a shift space is a closed subspace. But the idea here is that this shift space, if you imagine going on this graph here, any sequence of A's has to be followed by a sequence of B's of the same length. So we call this the A to the N, B to the N shift, or also it's called the context-free shift in some other literature. But it turns out that in the shift space, a path is only synchronizing if it passes through this V0 vertex. Or if it's represented by a path graph that does pass through this V0 vertex. And basically every bi-infinite path on this graph actually does pass through this, but there are elements in the closure that are not synchronizing, and there's actually countably many of them. And this is a little bit of a worse behaved example than the even shift, which is why I'm introducing it right here. But yeah, so this is just an example of another synchronizing system that's a little bit worse behaved. So not everything looks like the even shift. In fact, this the set of non-synchronizing points can be uncountable, even in some cases. Okay, so we have shown that synchronizing systems have a dense set of periodic points. So just to recall, the definition of a periodic point is just a point where if you iterate phi enough times on this point, you actually get the same point back for some n. So this is a very nice property of a dynamical system, to have this dense set of periodic points. So another thing that we have been investigating is using the K-theory of the homoclinic and heteroclinic algebras to get some information about the dynamical system. So that's sort of the whole goal of this research project is to think of K-theory as an invariant of the dynamical system and prove theorems about what, like if the K-theory is an obstruction, for example, to a dynamical system being of a certain class. So, for example, we know that if the tensor product of the heteroclinic algebras is not Morita equivalent to the homoclinic algebra, then the dynamical system cannot be a Smail space. So, for example, this is not true for the even shift, and the even shift is not a shift of finite type. So we can think of K-theory as being an obstruction in this sense to dynamical systems being a Smail space. The even shift is called a Sophic shift, which I mentioned, but in particular, Sophic shifts are the finitely presented shift spaces. And it turns out that every finitely presented shift space has its K0 group has finite rank. So if we know that the rank of the K0 group of the homoclinic algebra is not finite, then the shift space cannot be a Sophic shift. So this is true for this A to the n, B to the n shift that I introduced. Its K-theory is infinite rank, and so it cannot be a Sophic shift. And then I mentioned earlier that we have this ideal from the synchronizing points. So hence we get this exact sequence, short exact sequence of Cstar algebras. And so we've shown in the case of a mixing finally presented system that this synchronizing ideal is actually root equivalent to the tensor product of the stable and unstable algebras. So for some examples here, for the even shift, what this exact sequence looks like is the ideal, the quotient of the homoclinic algebra by the ideal is actually just isomorphic to the complex numbers because of the fact that we only have this one non-synchronizing point. There are also a lot of examples of finitely presented systems on surfaces. So it turns out that an expansive homeomorphism of a two-dimensional surface, which is orientable, only has a finite number of non-synchronizing points. So in this case, the quotient of the homoclinic algebra by the synchronizing ideal is actually just a finite dimensional Cstar algebra. And then, so to finish this all up, I want to go back to this even shift example. So it turns out that the stable and unstable algebra for the even shift can also be computed from a Bratley diagram that's similar, except we we only add words on the left or right instead of, I'll just go back. Instead of for the homoclinic algebra, we add words on both the left and right side at the same time to inductively build all these equivalence classes. But for the stable and unstable, we just are only adding words on the right-hand side or the left-hand side. And so the matrix that we get that encodes the edge relations in these two diagrams respectively are this matrix P superscript S and P superscript U. And I just want to illustrate that you can see this Morita equivalence in the Bratley diagram. So sorry for jumping around, but so if we restrict to these, I mentioned that these four vertices at every level, these give us the synchronizing points in the even shift. And so what we can do is restrict this matrix P to just those four vertices, and we get this submatrix of P, which is encoding the edge relation between the synchronizing vertices. And the thing to notice, so here I've denoted this submatrix as P sub sync. And likewise, for the stable and unstable algebras, we get a similar submatrix. for the synchronizing points. And it actually turns out that this matrix here is the tensor product of these two matrices here. So I didn't write any notation here, but this is PS subsync, PU subsync. And so we can see this Morita equivalence actually directly coming from the Bradley diagram itself. And yeah, so that is the end of the talk. Thank you.
So thank you for a very nice talk. Do we have any questions in the audience?
Yeah, I guess I have a question. Can you say anything about the space of invariant measures of a synchronizing dynamical system?
That is not something I know about that much. I'm trying to think if I've just in the literature if there's anything that I've come across.
I'm just asking because you said, right, that you always have a unique trace on the homoclinic and the heteroclinic parts. Is that right?
So that's only for the case of the Smail space.
That's just for the Smail space. Okay.
Yeah.
But
So,
that maybe is not the case here.
Yeah. So we don't know is the short answer.
I see.
So we've shown that in some, so if you have this mixing finally presented system, then we get the simplicity for these three C-star algebras, but we don't know yet about unique trace.
Right.
We do. So I guess there's a result from Karen and Robin on this like finite dynamic asymptotic dimension, if I'm saying that right. So we're pretty sure we can use that actually to show that the groupoid is immutable in this finally presented case. But yeah, so sorry, I don't know too much about the unique trace for the general case.
So for example, that the AF algebra corresponds to that Bartley diagram that you had.
Yeah.
Do you know what the trace space is of that one?
I do not know.
Yeah. I mean, fair enough. I guess you know maybe the K theory, so I guess maybe you could work it out. I don't know if it's so interesting. I'm just wondering.
Oh, I mean, I'm sure it's interesting. It's just
yeah,
not something I've thought about myself. It's on the to-do list.
Fair enough. Thank you.
Yeah, no problem.
Any other questions? So I actually have a question. So this I sync, this
yeah.
So in the Smail space, all points are synchronizing, but if you have all synchronizing points, do you obviously have a Smail space or no?
Yeah, you do. So
so then I think, so then don't you get, so is I think, does that clearly come from a Smail space then, I guess?
So I mean, I guess in the case of a Smail space, I sync is just
everything.
Perfect to A. Yeah.
But I'm just curious, like if simplicity, so I think itself doesn't correspond to a Smail space though.
Oh yeah, sorry. Yeah, that's a really good question. So I think itself, that's something we actually want to know. We don't know currently if isync actually is the C-star algebra of a Smail space. Yeah, which is something interesting that we've been looking at. So it turns out that finally presented systems are expansive factors of Smail spaces, and so we are trying to maybe leverage that to like construct a Smail space that actually is like the Cstar algebra of that Smail space is actually this synchronizing ideal. But I guess yeah, I mean, in general, the synchronizing ideal might not be unitable, and so
if you have like a simple mixing expansive mixing and expansive, and then the Cstar algebra is simple, does that imply it must be a Smail space?
so
I think would be everything in that case.
say it again. So if it's mixing and synchronizing.
Mixing and synchronizing, and then I-sync is everything. Is it a Smail space?
So it's, yeah, that's also not, because the even shift is a mixing synchronizing system. So
so it's simple.
yeah.
Okay, so I mean,
because it's finally presented. Yeah.
Good.
Yeah, I guess there isn't really like the recurrent properties can't really give you.
So I-sync can be everything, even if not every point is synchronizing, I guess.
Oh,
yeah, I guess that makes sense. Yeah.
Yeah.
Okay. And all suffix shifts, are they synchronizing?
Suffix shifts are synchronizing. Yeah.
And if you have something more general, do you get, like, can you have a Markov partition type thing like you can with the Smail space?
So yeah, the class of finally presented systems, like an alternate characterization of them, are the expansive systems that admit a Markov partition. But it turns out there are synchronizing systems that don't admit a Markov partition, but I prove in the thesis that if you have like a countable cover of rectangles, then which is obviously not a Markov partition, but if you have a countable cover of rectangles, then you are a synchronizing system. And then yeah, the finite cover of rectangles is the Markov partition. So
but, I mean, I guess there is a notion of a countable Markov partition, I guess.
Yeah, it's a little like there's a I know people work on like countable state Markov shifts, which is a little bit related to this example. If you consider like the unlabeled graph of this would just be a countable state shift space. But yeah.
Okay.
Yeah, I'm pretty sure a countable Markov partition refers to the state, the countable state Markov shift, but I could be wrong about that. I'm not entirely sure. I'd be interested to know, yeah, if you know more about that.
Not so much. Just sort of. No.
All right. Any last questions? And if not, maybe we can thank Andrew again for a very lovely talk.
Thanks for having me.
And next week we have Branimir Cetic, who will talk about differentiable Kunst-Pimsner constructions for Hermitian line bundles. So that's also on Zoom next week. So same time, same place. Hope to see you there.